This is the second class for Calculus 2 here on the last day of class. We didn't quite finish reviewing everything we wanted to review in the first section, so I'm going to continue the review here in the second section. And as I already mentioned to you guys, you should watch this video, or the first video, after class here sometime today to see the more full review of what you should know. I should also quickly remind you guys to do the course evaluations by Sunday. Make sure you get it done because that's the deadline. It is required, it's not extra credit. Easy points, but it is required. With you guys, I'm going to go through exam 2 mostly, and also talk about what you should know for differential equations. Though one student had a question at the end of exam 1's test. This was the last question on exam 1 from this fall. No, actually not quite the last question, sorry. It was a probability question, and the student asked me to do the mean because it wasn't working out for him. So let's go ahead and do the mean calculation. So this was the PDF. That's an exponential decay. This is an exponential model. In part C, we want to find the mean wait time. This is modeling wait times. To find the mean wait time, you need to integrate t times the PDF. It's analogous to a moment in a density and mass problem. What's the domain? All t greater than or equal to 0, so technically speaking, this is an improper interval from 0 to infinity. The PDF is what you see, 0.25 e to the negative 0.25. This is the improper interval to do. And this is one you'd want to use integration by parts for. We could bring the 0.25 out in front. We don't have to. We can include the 0.25 in the u. Let u equal 0.25t. You want to let b prime be the other factor, e to the negative 0.25t. U prime will be 0.25, and v will be 1 over negative 0.25, which is the same as negative 4 e to the negative 0.25t. Oh yeah, I integrated there, going from v prime to b. This is an improper integral as well, so you should include a limit sign in your calculation. The limit as b goes to infinity of the integral from 0 to b. U times v is this times this. 0.25 times negative 4 gives you negative 1. This first term simplifies to negative t e to the negative 0.25t. Evaluate from 0 to b. I better be careful and double check that I'm doing things correctly here. Yes, I think this all looks good so far. Minus the integral of v times u prime, the product of these two things. 2 minuses signs to make a plus. You do subtract an integral in integration by parts, but I've got a minus sign there as well, so I get a plus sign. The 4 and the 0.25 cancel again. So you're left with the integral from 0 to b of e to the negative 0.25t. As b goes to infinity, this part goes away. E to the 0 is 1, but you have a 0 here when you plug in 0. When you plug in b into this, you get b e to the negative 0.25b. The exponential decay overwhelms the linear growth. As b goes to infinity, that goes to 0 still. And that might have been something people had trouble with. When you plug in b and let b go to infinity, it goes to 0. That's just something to know. Exponential decay goes to 0 so fast compared to b itself going to infinity that this product still goes to 0. So you're just left with that integral And the antiderivative will be negative 4 e to the negative 0.25t. Evaluate from 0 to b. When you plug in 0 in this case, it doesn't go away. E to the 0 is 1. You get a 1 there. When you plug in b, it goes to 0 as b goes to infinity. It is exponential decay. The thing that's non-zero is when you plug in 0. And you're subtracting that part because the 0 is down here. So in the end, this should be 0 minus negative 4, which is plus 4. And 4 is the mean wait time, and the units would be what? Seconds? 4 seconds. For the mean wait time for the next car to enter the intersection. For the rest of the problem, I did briefly describe it, what to do, at the end of the last class, which will be at the end of that video. There were a couple of multiple choice questions in this problem related to the intuitive infinitesimal approach to things. If I put problems like this on the test, probably I would change the situation. I'd modify these enough to change the situation. This was about speed and distance traveled for both of these. Maybe I'd change it to be about, for example, what would be a good example? Maybe time, well, maybe t would still represent time, but maybe the quantity would represent how fast water is flowing into a tank, for example. So let's look at what the answers to these would be, and then you can think about how you might modify it for a tank, with water flowing into a tank. Y is the distance equals f of t is the distance traveled. T is a fixed number, and imagine dt to be an infinitesimally small change in time, just an imagination thing. What does this differential represent? That's a tiny change in time. There's the derivative of the distance traveled, that's the speed. This is rate times time, it's distance traveled. So it's the tiny amount of distance traveled, the infinitesimally small distance traveled over the infinitesimally small change in time. That would be the correct answer. If f of t represented amount of water in a tank, and its derivative then would represent the, say water is only going into the tank, so it would represent the flow rate into the tank, like in gallons per minute. And dt is an infinitesimally small amount of time. Then this quote-unquote product would be gallons per minute times minutes. It would be the infinitesimally small amount of water that went into the tank during that infinitesimally small amount of time. That's what it would mean in that context. So that would be an example of how I could modify the question if I decided to put this kind of question in the final, even to a new physical situation. If you watched the video from the first class, by the way, I was saying people should watch the video from the first class because we're reviewing different things in both classes. I'm videotaping your class here too. If you watch the video from the first class, you'll see I also went over a radioactivity problem that was on the mini exam, actually, I think. I could phrase this question in terms of the radioactivity problem, too, because there's still rates of change involved. There's still derivatives involved. Number 12 here is in the context of the same problem. The equation that the total change in y is the sum of the little changes. Think of the integral intuitively as a summation, even though technically it's not. This is how scientists often think of it. To find the total change in the quantity, add up the little changes, is how they think about that kind of equation. Where the integral is assumed to be a definite integral over an appropriate interval, though it's not written like one. How should this equation be imagined? Without looking at the possible answers in this context, I'm saying, okay, delta y, that's total distance traveled over a given interval of time. Not necessarily from time 0, but over some interval of time. To find the total distance traveled, add up the little distances. That's what I'm thinking when I look at that equation based on this context. Is that an option? to find the total change in position is the same as the total distance traveled during that amount of time. Is the choice A or C? Total. Need to add the infinitesimal speed. Okay, not add up the infinitesimal speeds. A is not the answer. You know, total distance traveled in this context is the same as change in position. So it's not the change in position versus total distance traveled that is the issue. I could have said change in position here. The key thing that's the issue is add up the infinitesimally small distances traveled. That's the thing. dy, as in this thing, represents an infinitesimally small distance traveled. That's the key to getting the right answer. By the way, I hope section 1 people are watching this lecture to get the full review here too. Because now we're going to move on to exam 2, which I started at the very end of section 1, and I started to say, well, you know, there's a bunch of true-false questions here in exam 2 at the beginning. And I circled the answers when you got them wrong on your exam 2, which I didn't really need to do, of course, since it's true-false. If you got it wrong, you would know what the answer is. But just for emphasis and just so people don't erase their answers and try to claim they got the right answer, I do circle it. So I don't think I'm going to go over these true-false questions. You should spend time thinking about them before you look at the answer on your exam 2. Maybe cover up the answers as you look at them and think about them. Like I've said already, I might change the wording slightly in one or more of these if I do put them on the final exam to make a true question false or a false question true, or maybe I won't change it. Or maybe there'll be a mixture, some might be changed, some might not be changed, if I do put these kinds of questions in the final. I'm not sure yet what I'm going to do. I haven't written the final exam. One thing you're going to see me say in the first lecture that I videotaped is one of the problems on exam 1 was a parametric curve problem, where people had to draw in position vectors and velocity vectors and find the distance traveled function. And I said people had trouble with it on exam 1. And I said, I think I'm feeling like putting this on the final exam because I want you to know it for one thing and do better on it. But also because we've been reviewing vectors, position, velocity, acceleration vectors, and distance traveled ideas here recently. So that was sort of another reason that that kind of problem probably will show up on the test. People did have trouble with that problem before, but should be better now, I think. I did add that you might have to draw the acceleration vector, and even draw the velocity vector accurately and find I hat and j hat components to it. You'll see as you watch that lecture, and you should watch that lecture. You'll see that information. Okay, that was something I emphasized probably will show up on your test. I did forget to mention here at the beginning, I'm also probably going to give 2 different versions of the test because there's 2 separate classes. Within each class, actually, there'll be people taking both versions that will have maybe some problems that are similar or the same and some problems that are a little different, perhaps. I'm going to try to make them equivalent in difficulty. But I think I better do 2 versions. Okay? So you don't know which version you're getting compared to somebody else. I still have to write these versions this afternoon. All right, this problem. Use the integral test to decide if this series converges or not. You'll need to use integration by parts. Show your word clearly and clearly state your answer. Basically, you want to take this function that you're adding up for integer values of n and make the n x and think of it as a real quantity. You don't have to change it for an x, but people typically do. And do the corresponding improper integral. And see if this converges or not. If it does converge, the integral test says that this one converges, the series converges, summation. If this integral diverges, the integral test says the series diverges as well. Doing this integral involves doing a limit, and it's pretty much just the same thing as this one, except no 0.25s. And the lower limit here is 1, whereas the lower limit there was 0. You don't care about the value of this, you just care about whether it converges or not. For the test, that is. It will converge, by the way. So the answer is this will converge. Technically speaking, there are extra hypotheses in the integral test as well. Like this function should be positive and decreasing. In this case, for all x bigger than or equal to 1, it is. Actually, when x is between 0 and 1, it's increasing. But that doesn't matter. All that matters, it might have sort of more of a hump here. All that matters is that it's decreasing once you get to 1. Decreasing to 0, in fact. And the integral does end up converging. So the answer is this one converges. Maybe I'd modify it to make it diverge. How might I do that? Maybe I'd say to do the integral test for this series, which is the harmonic series, which you should know diverges for a true-false question, but I could ask you to do the integral test for it. So you integrate 1 over x, which is positive and decreasing to 0. However, you'll see this improper integral diverges, and therefore this series diverges. So I could modify the problem that way, so that you need to use the integral test to verify a series diverges. This problem is about using the ratio test to decide about the convergence of this. The convergence of this series or divergence is not obvious to most people who are just learning the subject. You know, 2 to the n grows very fast as n grows, and so does n factorial. I'm taking the ratio of these things. Which one wins out? Does this series converge or not? If you try plugging in some values of n, for example, n equals 10, 2 to the 10th over 10 factorial is a pretty small number. 2 to the 10th is 1,024. 10 factorial is 3 million something, I think. So this ratio is pretty small. But that's not the issue. The issue is not, do the terms go to 0 that you are adding? They do. It's a different issue, though. Does the series, the summation, converge or not? Make sure you understand the distinction. It's not about whether the terms themselves go to 0, though if they don't go to 0, the series will diverge. That's the divergence test. You need some other test if they do go to 0, which it seems like they do. If the terms go to 0, you need some other test to decide about whether the series, the summation, diverges or converges. And the ratio test is typically what people use with factorials, problems that involve factorials. In general, you want to take the limit of this ratio, and if that limit is less than 1, then the series, the summation, will converge. If the limit is bigger than 1, then the series will diverge. If the limit equals 1, actually the test doesn't tell you anything. The series might converge, it might diverge. You can come up with examples where that's the case. In fact, for any p series, remember those things? Where p is bigger than 0. If you use the ratio test on those for any p, you'll get a 1 for the limit. So the ratio test gives you no conclusion for any p. But we know, and you should know for the final exam, you can put it on your piece of paper. You can put stuff on the front and back of the piece of paper. This converges when p is bigger than 1, and diverges if p is less than or equal to 1. When p equals 1, it's the harmonic series. That's a fact you should know. You can use the integral test to verify that. If you try using the ratio test, it doesn't work. The ratio test is not strong enough to help you decide whether this series converges or not for any p. Amazingly. It gives no conclusion. In this problem, I'm not going to finish it for you. I'll let you do that. You'll need to use the fact that, for example, n plus 1 factorial divided by n factorial, or maybe it's the other way around, simplifies, because n plus 1 factorial is the same as n plus 1 times n factorial, and we're going to cancel the n factorials. In this one, you will get a limit less than 1. You will get convergence. Okay? You should check that. Take the time to check that. This problem had 4 parts where you're trying to decide about convergence. No proofs, but brief reasons should be given. Sometimes more than one reason could be sufficient. At the end of lecture 1, they told me we should just make another video for lecture 2. I'm glad they told me that because it's taking a while to go through all this. But I think it's good. We're getting these kinds of problems, but I'm going to modify them, maybe even sometimes somewhat significantly. But these problem types for the final exam, as well as differential equations. Take a look at this one. That's a p-series, isn't it? P equal to 2. You can just use the fact that we know p-series converge when p is bigger than 1. That one converges. Probably the other option, that would be the best other option to use, would be the integral test. Ratio test will give you no conclusion. That's good to know, right? Because then you'd be wasting your time if you tried the ratio test with that. This one, not much of a change from that one. It's not a p-series any longer because of the +1 down there. If you try the ratio test with this one, it would also give you no conclusion. The limit would be 1. Could you use the integral test? You could. The corresponding integral would be this one, and this one does converge. The integral is going to end up involving arctangent of x. And arctangent of x does have a limit as x goes to infinity. The graph of arctangent of x has horizontal asymptotes, and this one's up at pi over 2. That's the graph of arctangent of x. And it's because the graph has that horizontal asymptote that this is going to have a limit as b goes to infinity. This improper integral does converge. This series will converge by the integral test. You also can relate it to this one. By adding 1 to the denominator of this one, I made each corresponding fraction, each term here, smaller than the corresponding fraction there. You can also say this converges because part A converges by the comparison test. Do you have to give a proof with the comparison test here? No. It probably would be reason enough if you just said, well, this is true when n is greater than or equal to 1, and the series from part A converges, therefore this series converges by the comparison test. Full sentence proof probably not necessary, I mean just after brief reasons. What do you think you should use for part C? What test would be most appropriate there? There's really only one of our tests that's most appropriate for part C, only one choice. Alternating series test. It is an alternating series. You might hope the alternating series test would work. It doesn't always apply to alternating series. For example, if the series, I'm realizing in the videotape you probably can't see all that. If you couldn't see all this, maybe I should move this over. I forgot about that, but I'm not having a camera person. There's what I wrote. Gotta write on the board more. It doesn't always apply if it's an alternating series. For example, if the series is this one, don't use the alternating series on the test on that one. That one diverges, and the quickest way to see why is the divergence test. These terms don't go to 0. If you write this out, you're doing 1 minus 2 plus 3 minus 4 plus 5 minus 6, etc. Those terms are not going to 0. This series diverges. So just because it's an alternating series doesn't mean the alternating series test applies. To this one it does. These things that are next to the negative 1 to the n plus 1 power. In the alternating series test, the book calls those an, though I think it's better to use a different letter like dn. And in this situation, to say an is negative 1 to the n plus 1 times bn. These bn's are going to 0 through positive values. And it is an alternating series test. It is an alternating series. Those conditions, the fact that the bn's are positive and decreasing to 0, and it is an alternating series, implies that this series does converge. Still not sure if they're in the video. I know we got part of the board, but not. What about this one? Just glancing at it, any gut intuition about what to say? You do want to try to work enough of these that you start to develop gut intuition about probably what to do. Those terms that are being added, what happens to them as n goes to infinity? Ignore the summation. You want to say?
Goes down and goes towards 0.
They go down. They don't go to 0 though. They go towards 1 over 500. Close to 0, but not equal to 0. These terms get small, but not small enough. They don't go to 0. That's enough to say this series diverges. The terms converge to 1 over 500, but that's non-zero. Therefore, the series diverges by the divergence test. Which, like I said, unless your series is not obviously geometric, the divergence test is typically the best thing to think about first. Do the terms that are being added go to 0 or not? If they don't, you're done. The series diverges. If the terms that are being added do go to 0, then you need some other test. I'm going to move this back now, but I'll try to avoid writing on the right side of it. I go through this stuff, pretty much everything I say is essential to understand. I try to choose very important things to say, to emphasize. You may want to rewatch this video too. All right, this one's about Taylor series. If your function involves sines or cosines or e to the x, typically the best thing to do to find the Taylor series is to use the ones that you know that you can write on your sheet of paper for cosine of x, sine of x, and e to the x. And that's probably the best thing then to do here for part A. It's pretty rare that the best thing to do is to use the general formula for Taylor series with the first, second, third, fourth, fifth derivatives. It's a pretty rare problem where that's the best thing to do. Okay? Usually these other tricks are better things to do. The series for cosine of x is, it only involves even powers. It's an alternating plus minus thing. 1 minus x squared over 2 factorial plus x to the fourth, excuse me, x to the fourth over 4 factorial minus x to the sixth over 6 factorial, only even powers, alternating signs involving factorials in the bottom. 1 is the same, by the way, as 1 divided by 0 factorial, because 0 factorial is 1. But I'm plugging x squared into the cosines, so each of those x's needs to be replaced by an x squared. Like this. Simplify and you're done. I say find at least the first 3 non-zero terms so we can stop after this one. But make sure you include the plus dot dots to get full credit. When I first taught the class, I didn't put that extra bit of directions, and people never put the plus dot dot dots, and it bugged me. So I'm saying that is part of the credit of the problem, is putting the plus dot dots. You need to indicate, you need to know and emphasize that the equality of this thing with the function is because of the pattern continuing forever. You can distribute the x squared through. X squared squared is x to the 4th times another x squared is x to the 6th. X squared to the 4th is x to the 8th times another x squared is x to the 10th. And then you should just know, you should write it on a sheet of paper, that the series for cosine of x converges for all x. Therefore, this one's going to converge for all x as well. For what values of x to the series converge to the given function? That's just something to know for all x. Could it be found in some way if you didn't know it? You could use the ratio test to find it, but it's kind of going to be tricky if you try to do that because of the powers of x going up by 4 each time, and the sign alternating, and the factorials going up by 4. It would be tricky to try to use the ratio test here to find the interval convergence. You should just know it's for all x. This one, for the 1 plus x to the 1/3, you want to use a binomial series formula. That in general is to find 1 plus x to the p, you get 1 plus p times x plus p times p minus 1 over 2 factorial times x squared plus p times p minus 1 times p minus 2 over 3 factorial times x cubed. If p is not a positive integer, and also not 0, this is a series that goes on forever and only converges when the absolute value of x is less than 1. If p happens to be a positive integer or 0, like 0, 1, 2, 3, 4, 5, 6, etc., it becomes a finite series, it becomes a polynomial, and it converges for all x. But typically we only use this when p is a fraction, for example, like 1/3 here. So the p is 1/3. I'll let you finish that one. It's going to converge when the absolute value of x is less than 1. Which, by the way, you should also know that's equivalent to x being between -1 and 1, in case that's not clear to you. Part C here involves knowing the formula for the sum of a geometric series. As it is the sum of a geometric series, this is in the form a over 1 minus r, where a is 5 and r is negative 25x squared. So what it must equal would be a plus a times r plus a times r squared, plus a times r cubed, plus etc. dot dot dot. As long as r is between -1 and 1, less than 1 in absolute value. Because the negative 25 there, that means x itself is not between -1 and 1, but we'll get to that. A is 5, plus a times r is minus 125x squared, this times this, a times r, plus a times r squared. R squared is 625x to the 4th, times 5 will be what, 3,125 x to the 4th. This is A plus A times R plus A times R squared. Converges when this is true. Absolute value of R is less than 1. That's equivalent to this being true. I can factor a positive 25 out of the absolute values and then divide both sides by 25. I can also put the square outside the absolute value sign. Then take the square root of both sides. This is equivalent to the absolute value of x being less than 1/5. X itself is between negative 1/5 and positive 1/5. That's the integral of convergence. That's also the values of x where this equals the original function. In B, it's arctangent of 5x, and to help you with this one, I said note that the derivative of arctangent of 5x is the same function as part C. I might do something similar in the final. The derivative of this is this. Therefore, an integral of this gives you this. Integrate this series term by term to get the answer. The fact that arctangent of 0 is 0 is going to mean the constant of integration is 0. I'll put a c there anyway initially, but it will be 0. Integrate the rest. Here's what you get. This does simplify to 625. And then this c is 0 since arctangent of 0 is 0. This will certainly converge for the same values of x. It's possible when you integrate a series that you can add an endpoint or two to the interval of convergence. Does that happen here? I think it does, actually. I don't remember if I expected you to know that on test when I graded it. Probably not. It does happen here. When x is positive 1/5, you get convergence. If you plug in x is positive 1/5, 5 times 1/5 is 1. 1/5 cubed is 1 over 125. The 125s cancel, you get minus 1/3. 1/5 to the 5th power is 3,125, right? And so you can think of those 3,125s as canceling, you get plus 1/5. I believe next you'll get negative 1/7 and plus 1/9, etc. It's an alternating series that does converge by the alternating series test. So you actually add 1 point to the interval of convergence here. But I think I didn't expect you to know that for exam 2, and I won't expect you to know it for the final exam either. If you plug in x as negative 1/5, it doesn't converge. Because then you get negative 1, minus 1/3, minus 1/5, minus 1/7, minus 1/9, which can be shown to not converge. If you wrote this answer down, it would be fine. Though technically speaking, just for your information, 1/5 is part of the interval of convergence. Here we go into some financial problems, maybe some actuarial problems here ultimately. Well, I see a lot of tank problems down there too. For some work done. Continually compounded interest rate of 4% per year over 5 years. Determine present value and future values of a discrete annuity. Finitely many payments. 5 of them, in fact, made once per year, starting right now at time 0 and ending with the last payment at time 4. Show your work. I think I remember people doing okay on this one. It's helpful to make a time interval here. times 0, time 1, time 2, time 3, time 4, time 5. Your payments start at time 0. You get $1,000 here, $1,000 here, $1,000 here, $1,000 here, and $1,000 there. For the present value, you are pulling all these back in time, so to speak. One of them is already where it's supposed to be. This one gets pulled back in time 1 year, this one 2 years, this one 3 years, and this one 4 years. Oops. For the present. So for the present value, you do this kind of summation. To pull this one back in time by 1 year, you've got to multiply by e to the negative 0.04, because it's a 4% continuously compounding interest rate, times 1 for 1 year. For the next one, you pull it back in time 2 years, so you multiply by e to the negative 0.04 times 2, etc. The last one, which is only one more, I guess, beyond what I wrote, you pull back in time 4 years. There's 5 terms in the sum. I could have made it 10 or 20 or 30 terms. Because the point is not to actually literally add these things up on your calculator, but to use the finite geometric series formula. Use this formula for a finite geometric series. If you write it like this, it's got n plus 1 terms. And I always remember the power of the common ratio here is the number of terms. This should be an n plus 1 if you write it in this form. Sometimes people write it differently. Either way is okay. Sometimes they write their last term as ar to the n minus 1 so that they have n terms instead of n plus 1 terms. And they make it the power of r equal to n in that case. Either formula is okay. They're equivalent formulas. This one's got n plus 1 terms. This one's got n terms. Use this formula as long as r is not 1, which it is not in these problems. R in this one is e to the negative 0.04. A is 1,000. But you, like I said, you should be able to do this for 10 or 20 or 30 terms as well because of that formula. For the future values, you're pushing them all forward in time to time 5. This one goes forward 1 year, this one 2 years, this one 3 years, this one 4 years, and the first one goes in time forward by 5 years. You need to multiply those by e to the positive 0.04 times the number of years you're pushing it forward in time, and then add all those up. And once again, you get a geometric sum that's best to use these formulas for. Like I said, most people I think got these okay, but just as a quick review over that. A water tank problem here. Find the total work done to pump the water out of the tank. I made the tank a right circular cylinder. I could make it a box instead. Or I could make it a cone. And a circular cylinder looks like this. A box is a box. It looks like this. More like a pool or something. No, pools are not perfectly like boxes. I could make it a cone like this too. To modify the problem a bit. In any of these situations, the key thing to think about initially is like a thin layer of the water. And figure out the approximate weight of that thin layer as a force. And the distance, the approximate distance that you have to take that thin layer up as you pump it out. Force times distance is the work for that thin layer. Add those up, you get the approximation for the total work, ultimately doing an integral to find the exact total work. Remember, we don't worry about intricacies like what do the water molecules actually do. They actually have to go down to where the hose is before they go back up. We don't worry about that. evidently okay to think purely in terms of thin layers of water being pumped up directly, as if you could pump up the thin layer all at once. The weight density here in English units is, for a cubic foot, is 62.4 pounds. That's already a weight. If I gave you the mass density in kilograms, which is what, 1,000 kilograms per cubic meter? Is that right? You got to multiply by 9.8 if I gave it to you in metric to get the force, the weight, in newtons in that case. But here the force is already given in pounds for a cubic foot. So like I said, you could call this width delta y. You want to find the approximate volume of the thin slice, and that's where the different kind of box affects it, or the different kind of tank. You might write this as delta y times a of y, which might be the best way to write it, or a of y times delta y. Actually, for the cylinder in the box, a of y is a constant function of y. The cross-sectional area doesn't change as y changes. Pi times the radius squared for a cylinder, and length times width for a rectangle, for inside the box. Those are constants in those cases. They don't depend on y. For a cone like this, though, you would get a dependence on y, though it would be a linear dependence. For the radius, at least, you'd square the radius. You got a radius here that depends on y, and you'd have to use like similar triangles to figure that out. You'd have to know the total height of the cone is, maybe like 10 feet, and this total radius here is maybe 6 feet. And that ratio 6 to 10 would hold also for the smaller similar triangle there for a given, if you call this depth y, this would be 10 minus y. So the ratio 6 to 10 would be the same as r of y to 10 minus y. And you could solve that for the radius as a function of y. And then the area of the disk would be pi times the radius squared. That would be the a of y, and you multiply by delta y to get the volume. Then, in this kind of problem, you'd have to multiply that by 62.4 to get the weight, which you could call delta F for force. 62.4 times delta V. Again, in the metric case, you take 1,000 times delta V, and then also multiply by 9.8, so you really multiply by 9,800. 9,800 times delta V. Pounds in this unit's newtons in metric. And then the approximate work done for this thin slice is to multiply delta F by y. For the total work, then you'd approximate that as a summation. And simplify your summation. Oops. 62.4y, a of y times delta y. Where again, for the cylinder in the box, a of y would be a constant. For the cone, it would be more complicated. And ultimately, this would be the function you integrate. If the tank were half full to start with, if this was 10 feet here, and the initial depth is 5 feet, y is representing the distance that has to travel upward. You have to integrate from 5 to 10. Because over this, the water down here would have to go between 5 feet up to 10 feet up at the bottom. Number 12, I said it satisfied the conditions of the alternating series test, and therefore I'm telling you this series converges. Part A, find and simplify S3. S3 is just the sum of the first three terms. So with this particular series, when k is 1, k minus 1 is 0, negative 1 to the 0 is positive 1. You're going to get 1 minus 1/8 plus 1/27. This one. That's S3. The error bound theorem, we want to find an upper bound for the absolute value of the error in using S3 to approximate the sum of the series. The error bound theorem says the absolute value of the error is less than or equal to the n plus first term that's multiplied by possibly the negative 1. This a sub n plus 1 is not the thing that is necessarily n plus 1 first term. It could have a negative sign in front of it in the series. But here in this inequality, you do not put a negative sign in front of it. So for this problem, this would be A4, where A4 would be 1 over 4 to the third, or 1 over 64 would be the answer. AK is 1 over k cubed without the negative 1 to the k minus 1.
Can you go over that with the actual numbers?
Say that again?
Can you go over that with the actual numbers? Like what you plug in to get homework?
Yeah, I mean, AK here in this problem is 1 over k cubed. So I plugged in 4 in place of k. 4 cubed is 64. The AK in the notation of the alternating series test does not include the negative 1 to the k minus 1. You can think of it, if you want, as being the absolute values of these things without the negative sign. And the theorem says this is going to be true. The absolute value of this error is going to be less than or equal to that. When n is 3, that means I put a 4 there. 4 cubed is 64. The actual error might be smaller, might be even, a lot smaller. And in part C, I have them find the actual. You find the actual error. And I think without absolute value signs here, and you still do actual minus approximate, so you still do S minus S3, but don't put absolute value signs in part C. Using this as the best approximation to 6 decimal places of the true answer. 13 was your actuarial problem. This is taking most of the time as well. Amazing. Well, there was a lot that we did, and we're trying to go over pretty much all of it here, including the first lecture. So get our minds around this again. We've got a lifetime random variable, the life of a person or a washing machine. We're pretending it's got a uniform distribution over the interval from 0 to 50. So little f of t is a horizontal line, height of 1/50th. That's the little f of t. Big F of t is an integral of that goes to the origin. It's going to look like this. And you get up to a value of 1 when t is 50. That'll be big F of t for the lifetime of the person or washing machine or something else. Z, this thing here, should look up here, nobody's looking, should look up here, and Z is a present value. Notice we are multiplying an amount, $1,000 say, by a negative power of e to the negative 0.02t. This washing machine is going to live till time capital T, and then you make the warranty payment of $1,000. What's the present value of that unknown future payment at some unknown time? If the unknown time is called capital T, that's the amount of time you have to pull it back to the present. This is the present value, and it's less than $1,000 if T is positive. assuming a 2% annual continuous interest rate. Annual interest rate compounding continuously would have been a better way to say that. We want to know about Z. Probabilities related to Z, the mean of Z, the median of Z. That helps us plan things financially. CDFs always can be thought about in probability notation in this kind of way right there. The probability of your variable being less than or equal to some particular number, little z. The capital Z represents the random variable. That's the unknown amount of the present value of the future payment at an unknown time. Think of little z as being something specific. Some specific value that you may find. You want to use the assumptions about capital T to help you figure out the distribution of capital Z. Use this equation. That's what I did there. Rearrange and use what you know about capital F. In particular, this fact here, how capital F is related to probabilities involving capital T. I'm telling you all this in the problem. The hard part is just getting your mind around it. Ultimately, you can find the CDF for capital Z by plugging in this expression into capital F and subtracting from 1. And it simplifies down to this thing right there. You can use either formula. Then, what you need to do. Part A says find little g, the PDF. The CDF is the integral of the PDF. The PDF must be the derivative of the CDF.
Yeah.
That's why we use the lowercase and capital letters, to remind you of that. The lowercase is the derivative. G of z, little g of z, is capital G prime, which is pretty easy. It's just 1 over z. Pretty simple formula. Notice the domain, though. That's important, actually, when you do the next part, or part C especially. Why is this the domain? Those are the possible present values, because if the washing machine fails right away at time 0, either the 0 is 1, and the present value of the future payment is $1,000 because it's right now. On the other hand, maybe it lasts 50 years. If you plug in 50 for t here, negative 0.02 times 50 is negative 1. You get 1,000, you get the negative 1 right there. That's the lowest it could possibly be. Lowest present value. To find this probability in part B, actually you don't need to use what you did in part A. You just use this formula. Calculate capital G of 1,000, of 900 minus capital G of 800. Done. Variance will involve a logarithm, then you can approximate it. Find the mean means doing an integral. Integral, in this case, of z times little g of z over the appropriate domain. Here's where you have to use the domain. 1,000 over e, or 1,000 e to the negative 1 to 1,000. This integral is easier than you might guess. Little g of z is 1 over z. You're really integrating 1. Z times 1 over z is 1. So you really just get this number minus that number for the answer. That won't always happen. This is a relatively simple one.